I keep going up and up, and now I'm at the point where, well, why can't it just sound like this guy at the opera company yesterday, or 2 days ago. Yeah. So, how's your brother?
He's in Argentina at the moment. But he's okay. You know, as you may know, his lead guitarist died.
I know.
The sort of has been a blow to his rock group, and they're taking some time out for a moment. Yeah. About a microphone, don't they? Like keep it at the back. No, all right. Let's see. I know. That's it does depend on this. Yes, I agree. Yeah. So, you know, maybe it that sounds like it's got some response.
Yeah, but it's not connected.
I can hear. Okay, please.
Then it's important that everybody is connected.
Yes. Use. Can you hear it back? You can. Back. So, good morning and welcome back to the second day of Physics in the City. And we're really delighted today at Phillips. Later in his life, he decided to devote some of his energies to opera, meaning music. Maybe we'll get to think about meeting. But anyway, welcome, Philip, and we're looking forward to your talk. Thank you.
Thank you, Piers. So, yes, I guess I just start with that. You opened it. I was a chemist for a long time, and I lost a very dear friend, Jan Zanen, recently, who also started off his physics career as a chemist. And that's something we bonded over. And we both ended up doing ADS-CFT. So I don't know if maybe that's the formula for doing gravity. Start off your life as a chemist. Anyway, I'm going to tell you about our most recent work on the Mott problem. And this is not a mistake. The title is upside down because what I'm going to suggest is that to solve the Mott problem, you have to really turn everything upside down. And the starting point is not what you would have thought. And because I'm interested in solving the Mott problem in 2D. And now if you say you solve the Mott problem in 2D, you better solve it in 1D. Okay, so what I hope to tell you about is this. So here's a comparison between this new method and the exact result for one dimension. The Mott problem can only be solved in one dimension exactly from the Hubbard model. So it's this new method, the exact result with beta ansatz, and it's just the percentage difference here. Okay, and here is the comparison. So this, and it's a function of this parameter n, which is what my whole talk is going to be about. So you can see this converges fairly rapidly to the exact solution with an error at n equals 12 less than 1%. Okay, so if I haven't explained this by the end of my talk, I'll start all over. But it should be clear that what I'm trying to do. Okay, now, what is it that one is trying to explain, and what makes Mottness hard? So here's what you would like to see in the solution to the Mott problem. Here are some quantum Monte Carlo simulations that we trust. And you see clearly an upper Hubbard band, a lower Hubbard band. The spectral weight at every momentum has weight both at upper, weight at two distinct energies, which means each momentum state is split into two. This violates, of course, the Landau correspondence, that in the interacting system, there are excited states that have no correspondence with the non-interacting system. And this is the thing that causes Mottness. And it causes very bizarre properties of the spectral function. For example, you will see zeros, since you have spectral weight at low and high energies. If you were to integrate this with just the moment 1 over omega, you should see a vanishing of the real part of the Green function. That's what I mean by zeros. Okay, so this is one of the things that you expect to see. And then with this, what you'd like to do is illustrate the Cooper instability. Okay. Now, you can't do this for the Hubbard model in 2D. So why can't you do this for the Hubbard model in 2D? Yeah. You have a half-fill band, and you're trying to get that. All this is going on in the half-fill band.
Trying to get an insulate.
Sorry, let me go back. Right. So this is the half-fill band. This is the non-interacting band right here. And at half-filling, you have a gap in the system. That's the Mott problem. And you're trying to get this without changing the size of the Brillouin zone. The two, however, are entangled. But the zeros are the real key to this. Okay, so you can't do this. Now, why is the Mott problem hard? It's hard because if you count the number of empty sites, because the kinetic energy and the potential energy don't commute, the number of empty sites is not a conserved quantity. It'll always be mixing with the upper and lower bands. And these doubly colored dots represent double occupancy. So you start with one empty site, and now you have 3 empty sites. And hence that's not a conserved quantity. And so you can't organize the eigenstates based on the number on the occupancy on every site. What this is saying is that there are quantum fluctuations in the number. And as a result of that, there will also be quantum fluctuations in the spin. Okay. Now, what one would like to think about is a ground state, which is nicely ordered. But we know that this is not the ground state of even the Heisenberg model because of the fluctuations. Okay. Now, because of the quantum fluctuations in the charge degrees of freedom, Mottness has a very weird signature. If you're just going to do, here's, for example, half-filling. This is exact diagonalization in 1D. The moment you introduce a hole, the spectral weight from here decreases, and the spectral weight from here also decreases. So you see changes in the spectral weight, both at high and at low energies. And this weight right here is called the dynamical spectral weight, because it depends on T over U. So this is what you would get if you doped a semiconductor. You just get one state above the chemical potential. This is what you see in a Fermi liquid. But in a Mott system, the spectral weight increases at least as fast as 2x. And because of T over U, the dynamical corrections, you will see that this weight increases faster than 2x. So that's what you're trying to get in any realistic model of a Mott insulator. Seamus, for example, has written papers on this 2x, plus the dynamical corrections, which is the hard part. But it comes about because kinetic and the potential energies don't commute. Okay. Okay, now, since you can't solve that, it would be good if you started off with a model that was solvable, and then you systematically improved it to get to the Hubbard model. And that's what I want to do. I want to start off with an exactly solvable model. It's local in momentum space. And you say, oh my God, that introduces all sorts of problems. And what I want to do is somehow move this model to the Hubbard model. Now, what you have to do is add in local dynamics. And that parameter n that I showed you in the first slide is the thing which includes the dynamical degrees of freedom, receiving the local dynamics, n of them. As you increase n, the model becomes the Hubbard model. But at every n, this model is exactly solvable. Okay. Now, someone who thought deeply about the Mott problem before noticed the following. He noticed that if you look at any of the densities of states of a Mott problem, right around 0, this slope is not equal to this slope, or this one's not equal to this one. As a result, there's whole particle asymmetry right around the chemical potential. And he was so taken by this, he said, I'm baffled by the almost universal refusal of theorists to confront this evident whole particle asymmetry head on. This is Phil Anderson. Okay, now Phil said lots of things about the Coupe problem. This is my starting point. So let's look at this paper by Anderson and Halgame, which it turns out has embedded in it an aspect of this dictum that Phil Anderson put down, namely that you really need to incorporate whole particle asymmetry from the get-go. Okay, so a Fermi liquid is a theory in which the kinetic energy does it all. If you were to add on interactions, any sort of forward scattering, one momentum to another, it would all be irrelevant. And that's why, and that's the statement then that Fermi liquid theory is a fixed point. And so I've written the kinetic energy in sort of a funny way with this operator that sort of makes it clear that there is a symmetry between the charge and the spin sectors, which there is in a Fermi liquid. Okay, now, as a result of this full symmetry group for a Fermi liquid, how many operators there are? There are 4 of them. Here they are right here. The full symmetry group is O4. And there are 2 subgroups of O4 which are relevant. There are proper rotations and improper rotations. Proper rotations preserve all of the symmetries of the Hamiltonian. And those form the group SO4, which is just SU2 cross SU2. There's an SU2 for the spin, SU2 for the charge. But the key thing is this improper rotation. Okay, now you can group these into two different groups depending on whether or not the matrix that rotates all of these objects has a determinant which is 1 or -1. Okay, so this group over here that has a determinant -1 is formed by the quotient of O4 with SO4, which is just the 2. Okay. Now, these are improper rotations. So what is it that these are doing, and why am I considering them when in fact they don't preserve all of the symmetry? In what sense does this system have this symmetry? And that's the deep question that Anderson and Haldane asked. Okay, so here are the 4 operators right here. And what I want to do is add and subtract them to form real operations, because it's easier to illustrate this matrix that transforms and goes between symmetric and anti-symmetric if I just add and subtract these to form the Majorana basis. So I'm now working with real operations. I'm just taking sums and differences, this one plus this, etc., and then the difference. Yes.
The fields don't all have the same momentum. You have C of P and C.
Yeah, that's right, that's right.
So you must between fields all of the same momentum.
I will get to this. I've written it like this. It doesn't make any difference if you write it in the spinor basis or just directly. It just, if you're a particle physicist, you would want everything written like this, so it's universal symmetric.
No, particle physics take fields all of the same momentum. It's really transform the thing in space.
Okay, if you can do it that way, if you want, you'll see what my statement will be in the end. And
for example, a Barnian Wertheimer spinner looks similar to this, but C of P and C dagger, C dagger minus.
so, oh, I see. You want this one to be minus.
Yeah.
Not here. Okay, so.
What about the lower one?
Well, the lower one, which I've interchanged, in which I have the opposite spin, yes.
But again, not minus and plus, but minus and minus.
Yes. Yeah.
That's unconventional.
Okay,
Okay, that's okay. I just wanted to know.
Yeah. Okay. It doesn't play a crucial role in anything I'm doing. So, okay. So, the simplest matrix that gives you the Z2 transformation is this one. It has 1 minus sign along the diagonal. Okay, now what does this do on this? Okay, so this acting on this just interchanges these two. Okay, so what we have then is a particle hole transformation for one of the spin species, not both of them. So the asymmetry is coming, or this symmetry, this Z2 symmetry, is coming about from just transforming one of the spins in a particle hole symmetric way. Okay, now if you looked at your original Hamiltonian, it's not particle hole symmetric. So when is it particle hole symmetric? Well, right at the Fermi surface, EP equals EF, Hamiltonian is equal to 0. And if it's equal to 0, I can make this transformation.
The slides on.
Oh, I didn't share them. I'm sorry. I didn't share them. I'm very, very sorry. What's this? Where is it should just be right here on. I see. Never mind. I got it. Share. Okay, good.
Can I ask a question?
Yes.
So, of course,
Yes.
so if you choose the one where you have the imaginary part of your complex fermion, it gives you
A minus sign,
particle transformation from one spin species.
right?
Which,
It-
if you
it-
take the minus one in the place where you have the real part of the complex fermion, it's an invariant subspace.
Okay,
So
so
there are certain Z2 transformations which for Hamiltonian.
now let me go to play, sorry. Okay, so I think I was,
If you put the dots at the top, you can hide.
hide more. Hide floating meeting controls. Okay,
And you can say
okay. To leave meeting? Oh, yes. Really? Okay. Good. I didn't want to leave the meeting. Okay, good. And it's okay. H equals 0. Okay, so what you wanted, Frank, is
So you put minus of
right. So you want to have it right here.
real part is
In any of these, you would be interchanging. But you'd be sending CP down to CP minus down. Okay, because this is there's a plus sign here. Okay. 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 So the important thing is that what they noticed is that for electrons right at, or excitations right at the Fermi surface, Fermi liquids have a hidden particle hole transformation, have an extra particle hole transformation for one of the spin species. Okay, so this just this goes to that, and this one just remains the same. Okay. Okay, so that is true. So this is the extra Z2 symmetry that's at the Fermi surface. Okay, so then their point then is, how do you destroy the Fermi liquid? Well, all you have to do is just destroy this extra Z2 symmetry. Okay. Someone lost the control of this. Okay, that's fine. Okay, so their point is, if you just look at this Hamiltonian, and I've just written it like this. Okay, what term do you add that breaks this Z2 symmetry? Well, it's sort of obvious. It's this term. It's a forward scattering term which you don't change the momentum. Okay, and so it's just you, this, and this. And note, this Hamiltonian can be written as just the sum on P for a bunch of independent momentum blocks. So it's exactly solvable. But the important thing, so this is odd under this Z2. If you only change one of these, this one goes to its minus. And if you look at the scaling dimension of this term, to treat this as an action that you want to look at a field theory for, this will have scaling dimension 0. which means all you're doing is counting the scaling dimension here, because the momentum and the time integration, all that cancels off in terms of how you scale. All you have is just the pure scaling of each of these fermions that make up these densities. This is scaling dimension -2. If the scaling dimension -2, this is a relevant perturbation. Yes. Yeah. Yeah. It is. That's why I set it up that way. It was always there, but ignored because it's non-local. I'm sure about that right now. What I'm doing is just what Anderson and Haldane said. And in fact, what I would like to do then is just see what are the consequences of this. Okay? It was always there, but no one considered it because if you look at Shanker's approach, he only looked at the local relevant operators. Okay. So there's a relevant interaction. And this has to define a new fixed point. Because it's taking you away from a Fermi liquid. What is it taking you to? Well, some of you might recall a paper in 1993. This is the Hatsugai Kohmoto model. Has anyone heard of this model? Okay. Well, of course, Peter's heard of it. We've been talking about this. Okay. But this way of understanding it in terms of the symmetry is more fundamental because it's telling you that it's the simplest model that breaks the symmetry. Now, it was clear to Anderson and Haldane that any model that has this 4 fermion interaction also breaks this local particle hole symmetry. And I'm going to come to that. Okay. It's just that this one does it explicitly. If you use the Hubbard model, it also breaks the symmetry, but it's subtle with that interaction. Okay. So the simplest case of the Hatsugai Kohmoto model is just anything that has a kinetic energy, which you just have the total particle density here. And then if you have this term, which is a repulsion, when you attempt to doubly occupy the same states in momentum space. But if you think about this, what this is doing is very, very simple. The moment you put 2 electrons into the same momentum state, you're moving that state up in energy. So if U is bigger than the bandwidth, you have an insulator. So it's the simplest way of thinking about the Mott problem. In fact, it's the simplest way of breaking a Fermi liquid, because what you have explicitly then is singly occupied states below the chemical potential. Okay. Which is not the case in a Fermi liquid. Yes?
Wouldn't be perfectly coherent eigenstates.
No. I mean,
Because
coherent in that sense. I see. Let me get to that. Okay, let me get to that. And that's why. So this model was written down in 1993. We were the first to put it together with the Anderson Haldane paper, which only had 3 citations when we started. And has anyone heard of this Anderson Haldane paper? Okay, there are less people who have heard of that than who heard about Hatsugai Kohmoto. Okay. Now, what does this model give you? So you can put anything in here. You can put in all of the stuff with topology. Then you can make exact statements about interacting topological systems, which we've done in a series of papers, but not today. Okay, so here you go. This is the green function. It has these weights, which are not C numbers. They depend on the occupancy. This defines the lower Hubbard band. This defines the upper Hubbard band. Okay? And notice, this does not equal this. So these 2 things can't add to give you 0. And hence you'll have zeros in the excitation spectrum. Which means when these bands cross the chemical potential, you can't just look at the residue. It turns out there will be a 0. Okay. So let's just look at this model. Here, this is the lower band. This is the upper band. And this is when they are well separated. U much bigger than W, you're half the length. This line right here is the surface of zeros, the Luttinger surface. Okay, and this is an insulator. Okay, now the excitations on this lower band I'm going to define by this operator right here. So this is the singly occupied part. And up here, the upper band is referenced only in terms of the part that's singly occupied. So it requires that each K-state already have an electron there. So these are the Hubbard operators, but in momentum space.
Philip, since you are local in momentum space, and the Hubbard modulus, of course, has an interaction local in real space.
Yeah.
This argument, you could also add longer range interactions in momentum space. Completely screwing things up.
It turns out if you were to do that and you did the power counting, you would end up with something that would take you away from Hatsugai Kohmoto. Okay? But let me get to a point which is related to that. Okay, so that's the Luttinger surface. Okay? Now, if you were to still stay at n equals 1, but U less than W, this band would drop below the chemical potential. And what you would have is this situation in which you have empty states, doubly occupied, which is the standard thing in a Fermi liquid, a singly occupied part, and it's only over the momentum where you have single occupancy that the Luttinger surface will live now, and a completely empty part of the spectrum. So you have three regions of occupancy in this model: omega 0, omega 1, omega 2. And that just corresponds to the momentum over which you have this demarcation of these occupancies. And in a Fermi liquid, you only have this part or this part, not the singly occupied part. Okay. Now, what you can do to see how general this is you can expand around the parts of these bands that cross the chemical potential. And you can, in this case, there'll be two such regions. Okay, this describes a metal. Okay, and you can ask the question, is the HK model, if it's special at all, it should be stable to any local interactions that you can add. Okay, and you can do the full RG for this problem, and you can show that the beta function is in fact 0. It works for either one filling surface around the chemical potential, or two, the beta function is identically 0. So in other words, if you were to add on local interactions in real space, you would not destroy this physics that this thing is a Mott insulator. For example, if you were to add Hubbard, it wouldn't change it.
The situation where you trigger of studio is it clear in some local models American?
Yeah, if you were to do the Hubbard model, you would see that in the special function there is. Yeah, that's how if you simply just count the particle density in the lower Hubbard band, you would see there are regions that look like that. Okay, now let me get to the actual statement that they made, okay? Because I've shown that it's much more general than that. This is the paper. And note what they did, okay? They said that the short-range repulsive interaction. Okay, now what's wrong with this quantity? There are no subscripts on it, okay? So if it's short range, it should have subscripts I, but they have no subscripts on this term. And they knew that any term you add would break the particle hole symmetry. It would break the Z2 symmetry. But the reason why they didn't put any subscripts is that they knew they'd run into a problem. The Hubbard model has a perturbative regime. So although it might break the Z2 symmetry, it's not a relevant perturbation. If you were to put momentum indices here, this is what Duncan told me last summer when I gave some lectures at Princeton on this. They didn't know of any model which was local in momentum space, so they never wrote anything down. They just knew that this was the minimum requirement. Okay, and they knew if they had such a term, it would be the most relevant term, this forward scattering term, you aren't changing momentum. Okay, so that is the term that is the most relevant thing, and there is such a model, and essentially what they were getting at is this. Even in the Hubbard model, you just construct the green function. The real question is the self-energy. Does the self-energy diverge? And for a certain locus of points in momentum space, it does. And if it does, you have zeros, and it doesn't matter the mechanism that you use to get those, you'll have the same physics. Okay, so there has to be a Mott transition. Okay, what does it look like? Okay, so this is, I'm going to call this simple model, where I just have pure non-local. It seems like it's completely non-local. Okay, I'm going to clarify that. And it's just one momentum index. And here is the evolution of the density of states for various values of u. For u equals 0, you have a central peak. And as I increase u, the height of this peak goes down. At a certain point, this peak, shrinks down, but then it gives rise to a gap in the spectrum. So u has to exceed a certain value, but it does so by a peak that is in the density of states. Okay, now this is half filling. So what does this look like? Okay, this looks like DMFT. Okay, if you look at DMFT, it starts with this peak, then slowly it goes on into this coherence thing, and then it goes into a gap. Okay, now DMFT is single site physics. Why does this model, band HK, which is the completely opposite regime, look anything like this purely local model? Yes. Here? Yeah. It's just how it's not universal. I'll show you generalizations in which this is not there. This is just in this simplest vanilla version of the HK model. Okay, but the important thing here is that this gives rise to this, to this right here, with a central peak. Now, if you take this similarity seriously, then it's telling you that perhaps there's a purely local description of the HK model, although it seems completely non-local in real space.
So you in the end motivated to disagree with beta ansatz in one.
No. I haven't even gotten this model. HK does not agree with beta ansatz. Okay.
Yeah, with your n addition.
Well, I haven't told you what that is.
My question was just for this, for example, how does the particular band structure come in, and so how robust is it against band structure and dimensionality?
Okay, so the HK result always has a finite value of u at which you get the Mott transition in any dimension, regardless of the band structure, because of the simple argument. The moment you start putting two electrons in the same momentum, that band starts moving up. When that's bigger than u, then you have an insulator. That would be true in any dimension. You have to have something much more complicated going on to get, for example, the real result that we believe in 2 dimensions for a square lattice, that there is no Mott transition. There is no critical value of u. That is not here. Okay, but I'm slowly developing the locus of ideas so I get to that point. Okay, now, so it seems like there might be a purely local description. Okay, now some are shocked by this, some are not. what we did is we said, okay, if it seems like the model is local, let's just look at the correlators in the system. They all, if you look at the endpoint, any endpoint function, you can construct in the HK model will factorize in terms of just the 2-point function. So this is what the 2-point function looks like. It seems like it's just decaying fairly quickly. So you asked this question, Frank, about something over here. There are no long-range correlations in this model. Okay, which is sort of surprising, which means that this model really does have purely local correlations, which means there should be some relationship between band HK and the single impurity problem. And that's because what really is band HK? Well, it's a bunch of Hubbard atoms. You have 4 states per site, and you have this momentum that's linking all of them. So it's as if you had a twist in the boundary conditions among a collection of Hubbard atoms. The physics on every atom is entirely local, and hence the model has to have local correlations. Okay, now this is the jumping off point. If we understand that this really is about a bunch of local atoms, 4 states per site, you have a huge degeneracy. And that's the problem with this model. There is this macroscopic entropy in the problem. Okay, and you can look at other correlations in the system, and you can show that all of these things are local. If the endpoint functions are local, by Whiteman's reconstruction theorem, the whole theory is local. Okay? Okay, so how do we extend the model? But no, it's fairly obvious. We need to start adding in local dynamics. So at every K point, what you have to do, yes? Yeah. Absolutely. Yes, you can. Okay? And it's because you can show that because momenta are not mixed in this model, all of the endpoint functions, regardless of what they are, factorized in terms of the 2-point correlation. So by Whiteman's theorem, the system admits a local description. Okay? So what do? You have to make sure that this term and that term don't commute. Okay, so what you do then is you add an index on each operator, which we interpret as adding n orbitals to each momentum state. Okay, and this is now this is now just whatever the momentum is, and the kinetic energy is. And here you have the interaction now between this particular momentum state and this local orbital index and this one. And so with each addition of an orbital, to keep the number of states the same, you have to decrease the size of the Brillouin zone. Okay? So n equals 1 is just the garden variety HK model. N equals 2, it shrinks like this. N equals 4 is like this. And as you let n go to infinity, this is the form of the interaction term. Just taking the limit in which alpha and beta are the same, otherwise end up with a different model, which I don't care about. As n goes off to infinity, all of the summation is just on the Brillouin zone has gone to 0. There are no K states left, which means this has to go to Hubbard. Which means I can go continuously from HK to Hubbard by increasing this local index n. I know that n equals infinity, I have to end up with Hubbard physics. Yes. Absolutely. Only at n equals infinity. Okay, which is why we are not guaranteed that we're representing Hubbard physics by any finite n. Very good point, yes.
Where does dimensionality come into? It seems the dimensionality of K is kind of irrelevant in the shrinking disk.
I'll show you. Okay. Yeah. Right, so we know we have to end up with this, okay? So, to summarize this part, what we've done is we've added local degrees of freedom. The model still is separable in each momentum sector. Okay, it still looks like this, which means my RG construction still works. It's only one momentum summation. This will still be described by this fixed point. This is now the orbital HK model. This has to map into this. In n goes to infinity, we have Hubbard. So this also goes to that. Sorry, this also goes to that. Okay, so my argument is this HK fixed point is really the reason why all of this works. These local summations over orbitals don't introduce any new momentum dependence. Hence, in the RG sense, it can't introduce anything that's taking you away from this fixed point. Okay? So that was the original, this is the original results I showed you. Okay, so this is now the ground state energy as a function of n, and this is the Hubbard model exactly with base ansatz over exactly that over that same number as a function of n. And what you see, n equals 1 is not on here because that's just completely the wrong answer. Okay, these local dynamics are systematically taking you towards Hubbard for a fairly small n. And the only computational cost is diagonalizing a matrix that's 4 to the n by 4 to the n. So it's 4 to the 2n. It's just one diagonalization. Since you can do this at any temperature you want, there's no imaginary frequency sort of reconstruction or anything like that. There's nothing like that going on. Yes. So yeah, we can do this, okay? But here I'm saying, you wouldn't have thought that it would converge so quickly. At n equals 12, which is a very reason anyone can go and diagonalize that, we're less than 1% from beta ansatz. Okay, so we know that the agreement will be at n equals infinity. Its scale is 1 over n. Okay. Yes.
Small n, there is a problem with
Right, at any n is lost because the way you think about H bound HK is that it's a bunch of Hubbard atoms. Well, that is a 4 to the n degeneracy. You look at the Hubbard dimer, that is a non-degenerate ground state. At any point, so what are we doing in this? It's actually a bunch of Hubbard clusters all connected by twisted boundary conditions. Yeah. Because since K is, that's the conservative number of states. And what you're doing is you're trading off K with these local, with this local index. Okay, now, so here is orbital HK, here's this result. Of course, the leading numerical technique in one dimension is DMRG. Okay, sorry. Let's just say you did exact diagonalization. You went exactly diagonalize a bunch of n-site clusters, which is what this ultimately is, but in this funny way of this K index, which is like twisting the boundary conditions. Okay, here's what you would end up. The answers are all over the place. So it's way better than doing exact diagonalization. Okay, now let's compare with DMRG. Okay, we can do that. This is what DMRG gives you for the convergence as a function of the system size. For the ground state energy of the Hubbard model. This is just the actual difference now, not the percentage difference. Okay, and you have to go to fairly large system sizes, but there's not a whole lot of difference here. So we're doing, in terms of DMRG, we're just as good. And it's cheaper. Okay, now the real thing is the charge gap. Okay, in the 1D solution for the Hubbard model, you know there's an essential singularity. Okay? This is the result that we end up with for the orbital HK model as a function of the number of orbitals. And this dashed line is the Bethe-Ansatz result. So this result right here. Okay? And the important thing is this small region right here around u equals 0. That's where the essential singularity is. And this is, so I've blown up here this discrepancy. Okay, we do get that u equals 0, the gap is 0. Okay, but we don't get this, at n, we need to go to a fairly large n to get this behavior, this exponential behavior. So we can't get that. Okay, so let's compare now with the leading numerical technique in one dimension, DMRG. And what you find is, they also have a problem at u equals 0 for an obvious reason, okay? You always have a finite size, and you're trying to get an essential singularity, which means the system size has to be bigger than than the inverse of this number, okay? And so in any finite size system, which is what DMRG is, you'll never get that the gap is 0. There's always some constant, they've just blown it up right here. Okay, so you do get this curvature. So it is looking like this, but it's always some constant offset. Okay, why are we getting 0? And that's because orbital HK is in the thermodynamic limit. Okay, yes.
You can do DMRG
Okay, I don't, well, for what value of system size?
and you can translate the invariant matrix. The scaling then is with one-dimensional correlation.
Right, but see, but then we just right.
Well, because it's never very good at the
Yeah.
that needs a huge one dimension to get.
Yeah. As they scale up the bond dimension, it really goes down. Okay. But
Then the axis not.
oh boy. Okay, I'm running out of time. Okay, this is an interesting point, but I do need to hurry up. It's clear I'm only going to cover the part on the Mott problem. Okay, now, as we know, that it's not just the charge sector that's relevant, the spin sector. Which means you need to look at the many-body gap in the system. We can go and compute that. And that has to be bounded from above by 1 over the system size, the LSM theorem. Okay, and here we go. As a function of n, this thing is scaling, but basically is 1 over n. So we do recover that. Okay, now the question everyone is asking is 2 dimensions, okay? How do you solve that problem? We can solve that one also. Okay, so here's a comparison of the double occupancy as a function of u for, let's look at the system we can realistically solve. A 2x2 or a 4x4. And the results, so this and this are fairly exact quantum Monte Carlo simulations. And as you see, if you look at, this is 4. So, right, this is 4, this is 2. You get closer to the exact results right here as you increase the number of orbitals. Okay. Now, yeah, so the complexity here is this. We are considerably faster than anything else. Okay, now let's look at the Mott transition. Okay, I told you just by adding in these local degrees of freedom, you've broken the commutativity of the potential and the kinetic terms. Okay, and that is sufficient to give rise to no central peak for any value of u. Okay, this is on the square lattice, and this thing just drops to 0 the moment you turn on u. Yes. it doesn't occur for any value of n not equal to 1. In other words, as you approach Hubbard, it's just completely gone. That is an artifact of one of local, single site physics. Yeah. So the DMFT result is not the generic result for the Mott problem in 2D. Okay? Now he's not here, so I can say that. Okay, good. It always opens a gap. That is our best. You can look at the numerics, that seems to be the case.
So if you did it in 3D, would you find the same thing?
Okay, we haven't done 3D. Okay, everyone wants to, okay, we have this playground now, we can pretty much go and do anything, okay? And somebody asked about changing the band structure. Yeah, go to a triangular lattice. There's a critical value of U. And that's what's seen when in other simulations. So we know we're getting all of the results that we are supposed to get. Okay. Can I just finish the first part of my talk? No, this is for the 2x2. We can't, so in 2 dimensions, we're stuck with just going and doing the diagonalization for that, okay? But even at a 2x2, we get the results that people are getting from huge simulations at, 1/100th the cost. Okay.
By 2x2, you mean alpha and beta are 2.
Yeah.
So that's where the dimensionality.
That's where it comes in.
Okay, so your alpha and beta.
Yes.
are just
Yeah.
if
Put them. Yeah.
you-
Yeah. Okay. Now the thing I advertised, the dynamical spectral wave transfer, we can get this analytically. Okay, this has never been obtained analytically before for any model. It's just entirely numerical. Okay, we have this greater than 2x growth of the spectral wave in the lower band. And if you had electron doped, you'd have this here. So it's completely symmetrical. Okay, now everyone knows that the Mott transition is accompanied by antiferromagnetic correlations. We can go and calculate the spin-spin correlator. Look at pi. Here it's as you decrease the temperature, this thing starts growing, and as you increase U, this thing starts to saturate here. So we do have antiferromagnetic correlations, which is a signature of, which is a consequence of Mott physics, but it's not the thing that's giving rise to all of the fundamental physics in the Mott problem. Okay, so we have that.
So this is for a square lattice type binding dispersion at half filling.
Yeah. Okay, now, is everything gapped? Okay, now we know that if we, that the spin sector should have gapless excitation, at least that's what the case is in 1D. Okay, so we computed the heat capacity, and the heat capacity doesn't exhibit an exponential terminal. It's basically algebraic in the temperature at low temperatures, which means there are low energy excitations. These can't be charge excitations, these are spin excitations. Now, because we've done everything analytically, we can just go and look at the matrix elements and look at the excitation energies and determine what is giving rise to this T-linear resistivity. Sorry, T-linear heat capacity. Sorry, T-linear heat capacity. That's another part of this. We've also done transport, but I'm not going to talk about that. Okay, so here's the big drum roll. Okay, it's a singlet, triplet that the highest, the lowest excitation has spin 1, the ground state is spin 0. And this is scaling like this kinetic energy squared over U. We just simply look at the points where that thing is going to 0. And that's where the gapless excitations are coming from. So these are spin 1 excitations they're gapless. Spin 1, so it's not a fermionic excitation. These are bosonic collective excitations, which are giving rise to the vanishing of the gap as you were to increase the size of the system. Okay, it turns out that is all I have time for. There's another part. So to sum up, we can get all the charge dynamics correctly. We can do the spin sector also correctly. And the Mott problem is twofold. You have to get the zeros, because that's leading fundamentally to the breakdown of the Landau one-to-one correspondence. And the spin sector is gapless excitations. But they aren't, you can't get this from any sort of slate particle type construction. Okay, it's really coming about from the collective behavior because it's a bosonic excitation. It's spin 1. Okay, now many of you might know the first paper we wrote on this. It was about the, I think this is really the first part. Yeah, you know, what can you understand superconductivity in a doped Mott insulator? You can in the basic HK model. That was the first paper that came out, I think, 2 years ago in Nature Physics, and I don't have any time to talk about that, but this is the new stuff, the orbital HK model, which allows us to quantitatively get the Hubbard model. So, thank you. Go to the, you start adding in orbitals, you will get this anti-parametric. So we looked at the spin susceptibility is 0, 0, and the pi pi. The function of n, this thing goes down, and 0, 0, the pi pi goes up. Okay, I mean, that would require looking at a particular kind of ordering, and everyone seems to ask that. It's like, is this enough for you guys? I mean, yeah, I mean, look, we can now go and do anything that everyone else has done, but we're just starting out, okay? Because we have a control way of doing this. You'd have to put in something that rates and look at an order parameter that rates translational symmetry. We can go and do that, but we haven't done. With what technique? It is what you put in. We aren't putting anything in. This peak in a pi pi is coming in spontaneously. Okay. It does. So it's at lower temperatures they can do. But that's at half filling. No, they don't. I mean, so if you stay at half filling and ask the question, what's the density of states at 0 energy? There are none. There is no density of states there. The moment you turn on U. at least for the smallest view that they look at. Right? That dynamical cluster, you know, this, what does Thomas Meyer do? It's ECA, right? Yeah, it's ECA, okay? Look, I know you're stuck with this thing that you have to have this peak there, but that is an artifact.
There's sort of a gap in the.
Yes, there is. Okay, can I show that? Okay, I will, I wasn't planning on showing that, but we have computed that. Well, okay. Yeah. No. Okay, so let me, the easiest thing to do is just to call up that paper. Twisted boundary conditions, main text. Okay, recompile. Okay. Yeah, let me just show you. I didn't have any transparencies on it because this is how old I am. Transparencies, slides on it. Here you go, Seamus. Okay. Share screen. Yes, share screen. I'm sorry, this is, and I can guess I can do it like this. Okay, good. Okay. Can you see this now? Excellent. There you go. Okay, here you go, James. Now, t equals 0. We can even include t prime. Okay? T equals 0. There is no dip in the density of states. It's only the t prime that you see the suppression of the density of states. And that is the pseudogap. This is stuff in the lower Hubbard bands, in the upper Hubbard band. Okay, it's the incoherent part of the spectrum, which has to be there because at each momentum you splinter the spectral weight into an upper and a lower part. That's Mottness.
Other question? So in 1D, the charge gap opens as its essential singularity.
Yes.
If you look at what it does in 2D, is it also an essential singularity or something else?
Okay, we did look at. Okay.
Saying the critical here is 0, then
Critical, okay, but the.
that's to the perfect nesting when it's nothing to do with not taking it.
Well,
In 2 dimensions, nesting is crucial for scaffolding. You don't put nesting in.
in other words, if I were to go to T prime, or if I were to go to the triangle lattice, for example, yes, if I, in fact, let me show you that. It's also in, actually, it's not in this paper, it's in the response to the referee. Okay, so, right. So, in that case, there is a critical value of U. Okay, so if you get rid of the nesting condition at half filling, you have to go through a critical value of U. Yeah, that's what one of the referees wanted to know. And we get that. Okay.
If you look for pairing in the orbital HK model, how would you pair across the different orbitals and
Okay.
any specified you would have to include linear terms?
Okay, so then I can give the second half of my talk. No, I did not ask you to ask this question. Frank was a postdoc at Illinois, and we worked together, although David separately, he was paying him. So Frank and I go way back. But let me stop sharing this and go to the good. And let me share my screen again. Okay, so the second half of the talk was all on superconductivity. Okay, so and it's this question, okay? And the thing that we'd written our paper on is, let me just go to more and hide this. Okay, good. For just the orbital model, sorry, for just the band HK model, no orbitals yet, we can show that there is a Cooper instability. Okay, now it seems as if adding, I think you would have to go to the same orbital, but you can work out the pair susceptibilities in each of the orbitals and just plot it out and see what happens. Okay, we can do that systematically. And that might be hugely relevant for the cuprates because we don't really know. Okay, now, what we do know is that if everything is controlled by this HK fixed point, the superconductivity that we get out of this is very, very different. Okay, it's one in which the Bogolubov quasi-particles are replaced by these things we call pions, and which are formed by the particle hole excitations that make up the Mott system, which are these composite operators, these C's and H's that I wrote down. Okay, so it's a combination of those on each orbital that you would be looking at then. Okay, let me just show one last thing from this, since Frank did me a favor. Excellent. You know, you were asking all of the questions I didn't show. Okay, so yes, here it is. I think I just need to go and share my screen again. Yes, the variation, and that's why superconductivity looks so different in this system. Let me just walk you through what superconductivity looks like in this system, because that was the second half of the talk. Okay, as Frank noticed, if in fact you do the Cooper instability for this version of the Mott problem, there are three different spectral regions, 0, 1, and 2. And as a result, the BCS wave function will have to have 3 parameters in it. Now, what's interesting is if you just have a product of k bigger than 0, just restrict to that, you will naturally write the BCS wave function with 3 parameters. Just a simple exercise, okay? But these are related, okay? Okay, in the HK generalization, they are not related. Okay, so this is 0, 1, and 2. And you can redo this problem with 3 variational parameters. Now, Frank, what you want us to do is expand that space considerably. I think we could do it. It'll probably be a 6 parameter variational calculation that can be done. Okay, but we haven't done it yet. And the gap equation looks fundamentally different. Okay, it depends on you. Okay, now, because of this, the excitations no longer look like these things as they do in BCS. Just a linear combination of a particle and a hole. Okay, because this does not annihilate that 3 parameter BCS wave function that I just wrote down. Okay, and these things are pions because that's with the order of our names in the paper. They look like this. So these are the basic excitations in the superconducting state. And they're very different. Okay. So the superconductor you go to is not a BCS superconductor if you start with a Mott insulator. And one of the things this linear combination can explain is this transfer of spectral weight from high to low energies that's seen in the Van der Marle experiments and the optical conductivity. The moment the system superconducts, there's a color change. And the reason there's a color change is that even the upper Hubbard band is also getting gapped. Yes. So let me just conclude the whole presentation with that point. Okay, so yeah, these are the things that are being gapped. Okay. Here's the van der Marle thing. I'm not going to go through it. But I just want to end with the really big picture that okay, this was all in the first paper. Okay, here are all of the differences with that Mottness induces on superconductivity. Yeah, just break the symmetry. This is the fundamental point. The moment you break that Z2 symmetry, the particle symmetry, you have a new fixed point. And this fixed point has a flow which is analogous to a Fermi liquid, but it doesn't go to the BCS. The only instability of this, you add on any local interaction, it'll always flow into this fixed point. Even if you add on Hubbard, that Hubbard is part of the deformation of this, you'll flow to a superconductor, which is this P1H superconductor.
Yeah.
Yes, that's a very good question. We looked at that because we have to go and do now the Fourier transform since it's easier for us. I don't remember, but we have computers. Okay, here's the thing. It's just the moment you add this term, it's just broken. Okay, so I can't. Yeah, it's like pregnant or not. It's one or the other. So yeah, there's no, once you break this particle hole symmetry, that's the fundamental. That's really the point of our second paper, is that the Mott problem does correspond to breaking a symmetry, but it corresponds to breaking a discrete symmetry in this Z2 symmetry. Okay, that's one of the things the student is working out. We don't have the answer yet. Okay, but there are all of the things that you would normally find up here in BCS. We are not finding it. We've cataloged all the properties in the superconducting state that just don't look like BCS. Okay. Actually, the first paper we wrote on the HK model was entirely on the entanglement. Actually, it wasn't the entanglement. We looked at one of the restricted von Neumann entities, which are like the entanglement. We have not done it for the orbital model, which would be the relevant thing here. So, but it's one of the things we have to do.
I mean, this model is a bit pathological. I mean, the starting model that you are half filling, and I mean, Steve Phillips did these papers that you get a recoupling ECS instability if you look at perfect nesting and so on. And this looks a bit similar. So, I mean, if you perturb away any time of going half filling, would you expect an additional fixed point?
Okay, so as long as you've broken this Z2 symmetry, There's no way of recovering Fermi liquid theory anymore. Okay,
You would still need a critical view to get,
it depends on what the band structure looked like. So for the Cooper band structure, I would say, well, if you had T prime, right, if you break that perfect nesting condition, yeah, there will be a finite value.
That's it. Thank Philip for a great talk. That means that 8 minutes to the hour.
Does the upper band break the gauge symmetry with that
Yeah,
weird mixture?
yeah.
But how would you find out that the?
You see, you would be looking for that. Of course you would, Seamus. I know you.
Turn off the mic.
Yeah, okay. Okay, turned off. Have I turned off the mic?
It's off.
You guys on? Okay.